So now we are on our last lecture of this module, that is risk conscious operation management. And since management of aging and bringing back the plant to original operating period is also a part of operational management, we are discussing plant aging management and relicensing. We are not leaving at aging management. We want an independent party called regulator. They authorize the plant operation, for the another 5 years or 2 years or 10 years, whatever this thing. The story before we go to this is, most of the nuclear power plants in the world, they have seen 30 to 40 years of their operation, and they have been relicensed for 60 years. So 40 to 60 years has already been done. It is a way of life in most of the countries, but going from 60 to 80, also there are some applications, and they are at final stages of their approval. So that means the plants which were designed for 40 years, now this is the importance of aging. And second observation about aging is, aging management is, in a fraction of money that is required to build a new plant, this aging management can be done. One of the experience has been that only 5% of the money and resources are required to bring the plant back to operation, operating the way it operated during the initial stages of 10, 5 years and all that, useful period. We will talk about those things actually. So here this presentation is a mix of a case study and giving the important aspects of aging management as part of the lecture. So initially we'll talk about the prerequisites, and then we'll discuss the case study in part B of this lecture. So as I mentioned, the plants used to be designed for 30 to 40 years, but there used to be a feeling, no, plant still can work for, if we do little aging management program, it can work for another 10, 12 or 30 years. So because there the design target itself was 30 to 40 years, The major observation is that most of the plants have been subjected to life extension refurbishment from 40 to 60 years. This we are talking about nuclear power plants, and this is a reality. For plants have been relicensed from 40 to 60 years. Further, regulatory provisions are being made to extend the life to from 60 to 80 years. So the net effect is, nowadays if a new plant is designed, it is designed for around 100 years. Because that confidence has come because of data is available, experience is available, and it has been demonstrated in not only one plant, because there are not any accident which we can attribute to aging phenomena. So it got validated, and now new plants are being built for 100 years. This lecture presents a risk-based approach for life extension. This is actually a case study I am discussing with you, where the life extension has been done, and this facility is a cobalt-60 irradiator. It is not as big as nuclear power plant, but for demonstration of the concept of risk-based approach to plant refurbishment and life extension, that has been validated over here. So you can see this figure. I cannot show many things, but in this irradiator, the products are irradiated and the gamma radiation, and the source is cobalt-60. Cobalt-60 is a isotope which is artificially made or through irradiation in the and then once you want to irradiate, then what will happen? If it is a farm product, the store life will increase actually. They will not rot on that easily. So that is a case, but let's confine ourselves to the engineering only. So when the products are coming around this cell, it is called irradiation cell, the source is lifted up, and the radiation field, because radiations are useful in many aspects of life. One is for preserving the products, especially when they are being sent from one country to another country, or in the same company in the warehouse for a longer time without deterioration. Then this approach is used, and now there are many irradiators available in India. Okay, so that we have. So cobalt-60 source is there. This is cobalt-60 source. This is irradiation cell. Product boxes, they are moving around this and going out. They get only a fraction of minute or second that for irradiation. Labyrinth is there for movement of and entry of the product and all. Ventilation duct, because ventilation has to be there. Otherwise, ozone formation will start in the duct, which is not good for health. It has got health consequences. Again, labyrinth on this side, that side. Then source pit. So like that. And then Um, uh, so, so let us first see the bigger picture. We had a plant, engineering plant, and probably you would have all known what is the bathtub curve. So in this bathtub curve, we have see initial period we call infant mortality period. I have named here initial experience when the plant trips, because fine tuning has to be done. Even though commissioning activities are performed, still the plant's performance comes to useful life only at this epoch of time. And this period is almost like 20 plus or 30 plus year period. Plant operates smoothly, and then the failures start, or plant unavailability starts increasing, and so this is a aging period. Now once the aging period starts, plant availability takes adverse impact, and that is where it is the right time to take a decision to shut down the plant, do the aging management and refurbishment activities, and start it back. Okay, so this is the time for extended maintenance activities, where major repair and replacements are performed, renovations are done. They are called refurbishment period. It is a time when plant is shut down for extended period, and all these major activities are taken so that we don't lose plant availability. And then finally plant availability, got shifted, it should be here, extended life plant. Then you can see extended life, and it could range from 10 years to 20 years, 25 years, 30 years, depending on what kind of refurbishment that we have done. Okay, and you see the benefit. Now at this point I was required to build a new plant. I was supposed to have a new plant because the deliverables are required. So the costing for refurbishment is between 5 to 10%. There could be individual experiences, but are even lower than that. And then plant comes to its life and performs its purpose. Meets its purpose. Okay. Now, what is refurbishment? Refurbishment is we are handling different type of system. This is a very important exercise because it gives a importance to various activity. Number one, it identifies the limitation of the aging management program that we will be doing, what kind of repairs we will be performing, what kind of replacement we will be doing. It, apart from qualitative, it requires a quantitative input also. So let us say, and this requires categorization of components. Let us say passive system, structural systems, so passive systems and structure. Actually, most of the passive systems or structures, they are basically life limiting component of the system. That means they cannot be replaced. But some conditioning or repair or it can be done on those things. And these systems are plant building structures, floor loading, mega structures, foundation, jetty platform. If we are having fluid flowing from sea, okay. So these are mega structures. So and here we can only do repair and repair work or reconditioning work. But they cannot be replaced. Replacement means it becomes life limiting. Okay, and I think most of the structures, their samples can be taken and they can be brought back to qualification, because wherever there are no testing, mega structure cannot be put to testing. So we will meet the initial criteria. So they are called qualification criteria, and we'll see, okay, they are as good as new now. So okay, they can be qualified now. Mechanical component structures, mega components. I think most of the component in mechanical category, they are meant to be replaced, right? From the mega pumps, heat exchangers, condenser, piping, valve and all, generator, and they can be replaced. But the important thing is their replacement should be available, and this puts a major resource consuming option, and that is where some becomes repairable and some becomes replaceable. So mechanical component we have talked, passive component we have discussed. Electrical components, compared to mechanical component, they are easily replaceable because they are diesel generator, breaker, most of them, so they are replaceable. Or if it is a very expensive component, they can, like transformer, a decision has to be taken. It is served for 30 years, whether we can go for another 20 years and all that. So that decision will be wholly based on the studies, aging studies that has to be performed, that are performed, and then finally a call is taken. Electronics and distribution, they are the easiest one to be replaced, especially if you use some detectors, special detectors. So depending on the kind of type of industry, but even they because they should not disturb the configuration of the plant at the core. At the core means where accessibility also is not there. So electronic cord panel regulation. In fact, here as a preemptive measure, the instrumentations are replaced every 5 years in some countries because they don't go to this obsolescence period and all that. So, and then specific system specific things like include nuclear, chemical, space. They have their specific requirements. Some component, sensor, shielding, protective layers, and their decision has to be taken by the expert. So this is an important part of aging and management program. So as we said, if I have to take a decision on some of the safety system, I should see how they have performed there, what was their unavailability. If unavailability was very high, then it is better to replace them. If there was unavailability was low, then we can take an optimum decision. But this quantified figure should be available for comparing these systems. And finally, they will have their own specifics. It can come in the where from this data has come, and these are various safety systems. What I am talking about is very important system structures and component in the plant, and what decision has to be taken. So certain inputs are available to us, and we have. So as a first step in this, all these things is to perform level 1 PRA of the plant. And identify the importance of the structure or risk significant of the structure, and that's how it goes actually. Without that, so PRA has been demonstrated to be working very well to have optimum program. And I told you, once the program aging studies form the major component of the program. So once we have done PRA of the plant, we have understood their performance requirement, then aging studies are performed. Aging studies are resource consuming things, okay, and depending on the size and complexity of the plant, required from 4 months to 1.5. So the refurbishment might require from 4 months for a small plant to 1.5 years. For every identified SSC, the data collection analysis has to be done, and remaining useful life has to be. We should have an idea of this key factor, that is remaining useful life, either through quality metrics, or through the some testing, or through so testing also will tell whether remaining life, like for cables, electrical cables, power cables, remaining life can be analyzed by taking a sample. For concrete, again take the sample and see how much deterioration has taken place after the new fresh concrete that was used, which were the documents were available. Decision to replace and repair is based on remaining useful life. A PERT and CPM chart is prepared while doing this project of refurbishment, because every activity is to be monitored and should be tracked. Any activity coming on critical path should be taking the priority compared to the other activity. The aging study document also provide approach for remaining life assessment or qualification of SSC for life extension periodic target. Before the actual work start, a ground regulatory approval is required. So like any other domain, regulatory approval is required for shutdown of the plant, for aging management, and after refurbishment, even for restarting the plant require regulatory approval. And then how much time should be given, whether the stipulated time has been given 10 years, let us say any regulator agrees with interval revisit to the regulator regarding performance of the system, and you get 10 years, which has happened in our case study. Okay, so like passive system, mechanical qualification, for how we do qualification for passive system, I told you take the sample, understand for decorporation, deterioration. For mechanical component, you see the performance, it will be reflected, and the qualification will be done based on, let us say there is a piping, how much is the remaining thickness there left, whether it is sufficient to go based on the previous data, it can go for another 10-15 years and all, or replacement is easier, and those kind of decisions can be taken. Let us see this case study. This paper was also published in Nuclear Engineering Design, and this was in 2011. That means this study was performed in 2011. That means 2021, the study's objective was validated, because the facility was operating till 2023, and again the same plant revisited regulators, and now I think the second spell of relicensing based on this extension has been. So as I mentioned you, this is the plant, Isomate Cobalt 60 irradiator. It had seen 30 years of life, and they wanted 10 years more extension, and a risk-based approach was adopted for it. A document was developed, okay, and next 10 years extension was requested in this, and then the major procedural steps like performing PSA, uncertainty, and all these things where the PRA model was developed, and then remaining life statement based on the compliance of radiation protection goals and testing. results were put up, and this is how it was there. When you perform PRA, you have initiating events, you have safety functions and safety system, engineering features, and then we have safety system unavailabilities that tell us what is the performance of the system in last 30 years for this plant. And one event I'll tell you, for power failure 1.9 per year, and for this event tree was developed, and then finally its uncertainty were characterized, which was 1.24 to 2.66 chi-square data. You know these things, how we have done it in PRA earlier, and then identified system, mechanical system, how they were qualified. The ASME code 3 was used to qualify them, and here in some remaining testings were done for mostly for electronics and electrical system, and some were replaced also. So these are the list of the component that we have. And then so as I told you, on the class 4 power failure, how if you vary and how it is impact the output in terms of risk consequences of the per year. So that was seen and it was mapped, and finally the results risk profile shows that whatever permitted for irradiators, it was very dose consumption was minimal or at all. This was for ozone. If it forms in the cell, what is the impact? So safe entry time was identified here, and this was 2.5 minutes around, or less than 3, and these parameters were developed, and with these results the regulator agreed, okay, this plant can go for life extension for 10 years. The facility director again took for explanation for 2024. So what, in short, we are telling you that PSA methods work well as a risk-based approach for even aging management of the facility or nuclear power plant, and same can be applied effectively for process system, mining system, railway system, and all that. These are the references you can see. There are, I think, 50 references that are there or more. You can refer these things if required. Thank you.